systems, the whole shooting match. So, Broadcrown, it's a company, been going for 40 years, formed in 1976, manufacture, supply and install and commission of generators, diesels, and it was a global market, had international sales. In about 2012, I think Broadcrown, as it was, had something like £48 million turnover that year. So, but it was bursting at the seams, quite frankly. We have two key manufacturing facilities, one at Hixon in Staffordshire and one in Newtown in Powys. The Newtown one basically manufactures units up to about 700 kVA and then would send them to the factory if there were any upfit elements or any witness testing aspect associated with those generators. So they'll shell out standard units and then fire it to the Hixon factory for any upfit or witness testing that there may be. The Hixon factory would then do all the high horsepower units. So we basically provide power from 6 kVA to 3 MVA prime, 3.3 MVA standby. So that's just a brief history. Broadcrown established 76 and expansion overseas in 2000. They basically overexpanded, got into financial problems, and were taken over by JCB in 2015, September. So acquired by a $4 billion multinational company. So now we have no realistic issues because we're underpinned by a major financial company. They have grand plans. By 2020, they're expecting the turnover on the power products division to be in 300 million per annum. So that's quite a lot of units.
Do you have to paint in yellow?
Yes. Well, funnily enough, the Broadcrown units were originally yellow and black anyway.
Oh, right.
So it actually tied in quite nicely. And JCB had been looking to acquire Broadcrown for a couple of years. The power products division of JCB was actually started in 2006. So it's been going on just over 10 years now. And they supply product through their distribution network, their dealer network, as such, to supplement the construction side of the business. So sometimes that works very well, and there are some dealers as well that supply generators, supply and install as their core product, but in a lot of cases with the dealers it tends to be the secondary stream product as such. So obviously if they're bursting at the seams on the construction side, sometimes maybe the focus drops off on the generator side, and that's an inevitable aspect really. So, $4 billion business, number 2 in the world by construction, 22 plants worldwide, 12 of which are in the UK, 24 subsidiaries, global network, dedicated dealers. So basically, since the takeover, amalgamating the two and using the, for instance, in territories where Broadcrown had a very strong brand, keeping the brand there, adding JCB underneath it. It's like, if you're familiar with alternators, there's CGT in Stamford now, they've got Newage and Stamford brands which they still retain on their products because of that knowledge and that how it's deemed in the market, because there's so many companies get sold left, right and centre these days. The branding is very important and key. So for instance, where JCB product is strong, that is the primary brand element as well on some of the generators. So that gives you an idea of the structure. JCB Broadcrown, we've got the two manufacturing facilities, the Newtown and Hixon facilities on the left hand side there. We do the global projects, and then we've got the associated service and support as well. So the key thing is the manufacturing, the design and engineering, commissioning, sales, installation and services are all essentially under one organisational roof. We have our own panel building facility, we have our own software programmers, we have our own commissioning engineers and mechanical and installation teams. Where we have an overcapacity, we then bring in subcontractors. However, they know and are very clear on our expectations. So that's how it works. So, the flexibility as well is there because we can use different engine manufacturers. And you'd be shocked at the actual differences between some of the engines for a given output, the airflow differences, and also the performances for load acceptance, load steps, etc. It's quite surprising. So again, the range, 6 kVA to 3.3 standby, power outputs. 50 and 60 Hertz units. We'll use Mitsubishi, the Yanmar, the John Deere, the Volvo, the Cummins, the MTU, Perkins, and we use as default Stanford alternators, which are the 2/3 pitch. If you've got an existing site where they have 5/6 pitch alternators, we've got flexibility to use Leroy Summer or an alternative manufacturer also, where some of our competitors do not. So, we also offer a comprehensive range of control panels. We tend to use CIBSE on the standard smaller range units, and maybe go to Colmap on the larger units where you want to fill in bells and whistles. It might be a bit more complicated on the distribution systems. We also can use DIFE and others, so again we've got the expertise in-house, which again is key, I can assure you. We can offer silencer options, fuel transfer systems, load transfer panels, again what you want. It's very much dependent on, often my first input with any project is at the consultant stage, where they'll give me a call, they'll say, okay, these are the loads, or this is the space we've got available, this is the attenuation level, this is the output we require, how do we best design that? So I'll give them options on maybe multiple units as opposed to a single unit. If you've got 3 MVA power requirement, often it's best with 2 smaller 1.5 MVA units. One, if one's being maintained, you've still got half the power cover. Things like that come into play. The power density is one thing. Obviously there's a lot of pressure. Sometimes we're putting units within buildings and you've only got very limited space available with the high power output requirement. But again, we look at the constraints associated for a given site and come up with the best options for the customer. So, one of the key things again, kVA, kilowatts. Funnily enough, with diesels you talk kVA, with gas sets you talk kilowatts. Don't know why, but it's just the way it is. Normally it's 0.8 power factor anyway. We do LV and HV systems. The main thing to consider is the running parameters of the unit, and that ties in with the ratings. So the ISO 8528 definitions tend to be the most important things to be aware of for the suitable selection of the unit, how long you want it to run, etc. So for instance, just picking a particular size of generator, a KTA 38 Cummins unit, KTA 38 G5 designation will give you 1100 kVA at standby rating, it'll give you 1 MVA at prime rating, and it'll give you 770 kVA at COP. Now these are the key things related to ISO 8528-1, and it's one of the most important things I say for customers and consultants to have a good understanding of, so that you can designate an appropriate rating for your generator. There is a key thing. One is the application, and then the other is the rating of the genset for that application. So your application may well be standby for a hospital or for, say, a new building. A new building might be a life safety unit where if it's needed, it's a highly unlikely event, but if it's needed, it might only need to run for 3 or 4 hours for people to evacuate the building, that's it. The fire officer's happy with that sort of period of running. So it's a standby application, but you can have a standby rated set for that standby application. Now if it's a hospital, say an 11 kV ring, a hospital, say Peterborough Hospital has 6 MVA of generators there. It's an N+1 basis, in other words a spare set, so the actual maximum power requirement they deem they'll need is 4 MVA of power. Now the rating differences are key. For instance, if you have a substation that goes down, that hospital wants those sets to run at a variable profile for an unlimited period of time. In other words, it's not limited. So, emergency standby power, by the definitions of ISO, it has a capped limit per year of 200 hours of running, an average variable load of 70% of its rating. So, basically 70% of 1100 is its maximum average variable load, but there's a cap of 200 hours per year. The reason why you select a unit with that limit it affects the engine driver itself. If you want it running for a longer period, you might end up with a larger engine basically for a given output. So standby rated, prime rated power, again average variable load of 70% of its rating, but PRP definition means it can run for an unlimited period of time or period of hours per year. Okay, so there's no cap on the running for that, which is key. Often when they churn them out in the factories, you'll either be able to just put an input on the control panel, whether it's a standby or prime rating, you just put the parameters in. So in other words, you can't tell the difference between the two, and you can easily plug in one or the other with those. The different one is the COP. COP stands for Continuous Operating Performance. In other words, that'll give you 100% load for an unlimited period of time. That tends to really push you towards gas sets, where you want a base generation, you want them running 24/7, and then you might be importing a top-up, you know, from the mains as a top-up for any deficits or maximum loads that you have on a building profile. So often, I haven't sold one diesel set that runs on a COP basis, to be honest. Okay, now there are different market sectors here. There are construction side, and there are also data centres. So there is special rating that's given for data centres, which relates to a COP, because in context of data centres, the likelihood and, you know, their N+2, 2N or aspects related to that site, the surety of power, what they'll do is often they'll take a prime rated power unit and rate it as a continuous COP unit for a data centre application. So there are exceptions to this. But the point being, for any site that you've got, the key questions to ask are, how long do you ever expect it to run per year? Worst case, you know, what is the real application? If it's a hospital, I'm sure it's probably going to be, or, you know, a major hospital, you'll want PRP rated set, prime rated set for a standby application. So I hope that gives you a rough idea. The reason why, for a given size of unit, you derate the output, it's literally to do with life of plant. You expect this to last over 15 to 20 years. The key thing with this running period, it affects the engine driver itself. So if you actually said to me, you could see this KTA 38, 770, if you said to me, I want a generator to run at COP at 1 MVA at COP, that probably means it's a 50 litre product, 50 litre engine you'll need, as opposed to actually a 38. So it's the key thing is the effect on the engine driver itself, and it's to do with stress of the components, the running and the life of plant. The reason why you've got either or on this, again, it's capping the limits on the stress, certainly for that one, and because you're running this on a limited basis, average variable load, it's derating it, keeping it within stress limits. So it's probably covers that nicely. Application itself, it might be automatic mains failure, you might have a set running in island mode, you might have multiple sets synchronizing and paralleling with the grid for a short-term or long-term basis. So there's very much different applications and requirements that you want for the unit. One of the other key things that comes into play is its load acceptance capability. Typically, of the high-end generators we can supply, the Mitsubishi, the Perkins, the MTU, the Cummins, they'll all take a cold load acceptance, typically of about 50% of its rating. So say this unit, a prime rating which is 1 MVA, it'll take a 500 kVA load step. Okay? Some units will take 100% load step and not stall. The reasons behind that are the Cummins unit and the MTU units, they comply with the NFPA 110 specification, which is an American origin spec, which means for fire pumps and, you know, fire situations, basically they want to bang full load on this and have it not stall. So some of these sets of generators really do have the legs to take the 100% load hit, but it's not recommended, but it's nice to know you've got it if you ever need it. Now that in turn relates to a higher performance capability with taking a load step. Okay, so
Are these all high-speed diesels?
1500 RPM units, all of them. Yes, they tend to be the only ones that we supply now for these type of applications. So again, the sets are very reliable. So if, for instance, you had a start signal on a unit, assuming it starts first crank, it can be up to 90% of rated voltage and frequency within 8 to 10 seconds. So it'll, you give it a start signal, it'll actually, when it's up to 90% rated, it'll give a signal to say, I'm ready to take load, which can be your point where you use the old transfer switches or just close some breakers to start applying. So for instance, hospital specifications, there's an old specification called C44, and it used to differentiate between turbo diesels and also non-turbo units, but the non-turbo units, the limit was 15 seconds where you're supplying power at LV level. So if you've got an 11 kV or 11 kV generators and it's supplying power in a ring, once you've got the loss of mains and the start signal, the specification requires that you're supplying power at LV level. So the generators close onto a bar, they supply the power to energise the transformers, who in turn have their breakers closing, and that's supplying the power at LV level within 15 seconds. And it's proven time and time again you can do that. There are various options. There's dead bus paralleling, or there are various starting scenarios you can have to get the sets to either excite together, or actually first one closes and the others may sort of very quickly synchronise and parallel with that first lead unit. There's quite a few ways of skinning the cat, but either way, 15 seconds is quite impressive, really. Yes?
What's the difference with an MTU set? How does it actually take 100% load seconds?
The NFPA 110 specification means, by design to comply with that, it literally is designed. So you could say it's over-engineered compared to some of the others, quite frankly. Manufacturers are very, very cautious that you run within the operational envelopes that it's designed, for obvious reasons. The liability associated with these products can be horrendous. And that's why they're very clear on the definitions, which give you, for instance, in most cases, the PRP gives you a very, very nice, large operational envelope. If you're running 200 hours per year, the problem is, with this specification, 8528-1, it's very good bedtime reading curing for insomnia, I can assure you. Because what happens, within each one of the definitions, they go into a lot of detail, and then at the bottom of that, they'll put, unless the manufacturer stipulates otherwise. Well, guess what? He often does. Cummins has a limit of 200 hours per year, and quite a few caveats for their engines. Perkins, or FG Wilson Perkins product, they'll actually warrant that unit for running up to 500 hours per year. So that's why it's important to recognise the specification, but also, most importantly, to really pay attention to the data sheet related to that engine alternator combination, because that will give you the specifics of that unit, which may be over and above the ISO standard parameters. So again, I can't emphasise that enough. So, load acceptance. Sorry, firstly, how many electrical engineers? Okay, and the rest mechanical? Okay, alright, I just need to be sure. Please fire the questions in. Load steps. The best way, best analogy for me, I know this is bad, but whatever. Car driving along at 50 miles an hour. The load step is literally hill, enormous great big hill, depending on the size of the load step. And what happens as soon as you hit that hill, if you want to maintain the same speed, you're banging the pedal to the metal to try and stop your drop off of speed and then recover back. Same situation applies. If you're synchronized with, a single set or synchronized together as such, that's exactly what happens when the engine alternator sees the load. What it'll do, the fuel rack will open up, depending on how aggressive it is, what the parameters are as such, pedal to the metal to overcome that load step or that hill that's just been applied. when the set's been running along, and obviously doesn't necessarily see that's coming, so it has to react very, very quickly. Now often, on the data sheets, what you'll find is, let's pick a unit, 2 MVA prime, which is a QSK, Cummins QSK60G4 generator. Now that will use, a bit of an anorak I'm afraid, 396 litres per hour, 100% load. Okay, but what it'll actually, that's actually how much it uses when it's running at 100% load. But what you'll see is the fuel flow will actually be something like 680 litres per hour. So there's a flow and there's a consumption. Now the reason of the distinction between the two, say you've got a day tank here, generator here, you've got fuel feed line here, drop valve, spill return. That's your day tank. 4-hour day tank normally I'd recommend, unless circumstances dictate otherwise. I'll tell you why in a few minutes. You've got fuel feed line that comes through to this unit here. There's basically, the best way of describing it is that fuel comprises of 3 considerations. 1, the current load acceptance, or the current load of the unit. 2, just in case you put the pedal to the metal, what it'll do is it'll react and slam as much fuel into those cylinders as possible. The reason being, of course, it wants to recover from that load and stabilise as quickly and effectively and efficiently as possible. So it's got more, basically, current demand of fuel, surplus of fuel just in case you put the pedal to the metal. And the third element to the fuel is it uses fuel for cooling of the injectors as well. So that's why you have a spill return. So you will literally be circulating 680 and you'll get a net return into the unit, into the day tank. Now I say day tank, I'm showing that as a freestanding tank. It's terminology again, day tank, brake tank, belly tank, whatever you want to term it. It's a local tank to the unit because almost all units, generators these days, 1500 RPM units, will use the fuel for cooling the injectors because of the efficiency aspect to consider. It'll always have a spill return. So in other words, the fuel will always go back to the tank at an elevated temperature. So if you've got a bulk tank in the basement and you're supplying fuel up to this through float switches, you've got a high and a high. High generates the alarm, high's the demand switch off. You've got a low and a low. Low generates the alarm to indicate low status. So in other words, it's cycling between the high and low float switch. Okay. The concern you've got is if that tank is not a sufficient reservoir, certain running and load conditions, your spill return, high temperatures, light load conditions, that fuel will be returning at elevated temperature. You'll get a creep up on the fuel temperature if your reservoir is small, and you can actually get the fuel going through and even get some pre-detonation issues. So I always say, 4-hour day tank unless situation and circumstances dictate otherwise. And it could be a belly tank, day tank. These tanks can easily be slid at the side of a unit in a plant room or a container out of the way, again by design, suitable placement with flow and return systems. You also have something like 2.3 metre maximum head return height for your delivery system from the centre line of the crank on the genset. The reason why, if you get an excessive head height, you get resistance. If you can put a non-return valve in there if you like, so you don't get spill back, because that's the situation. So when the set shuts down, all the fuel goes back and you get a run on. But if you put a valve in there, you've increased the resistance, non-return valve. So the best thing to do is just keep it below 2.3 metre height, centre line of the crank, always. Spill return always to a reasonable height. You'd be surprised at how many sites have not considered that correctly. Okay, so you've got a bulk tank in the bottom, you'll have a fill point cabinet maybe to an outside wall somewhere. That fill point cabinet, the old tanker driver comes along, 2-inch connection, bangs it in, he'll have his gauge, he'll have his alarms on that, he'll fill that tank to whatever is the set limit, either percentage or capacity indication of litres. Normally that line is single skin. The reason it's single skin is because it's not a permanently wetted line or pressurised line. It's basically the tanker driver will fill it up, he'll blow air through then to clear all the fuel back into that belly tank. Job's done once it's got up to the gauges. But often what you have on these tanks in the basements, wherever they are, you'll need a vent line as well. The vent line used to go back to the fill point cabinet. The reason being, just in case the tanker driver wasn't paying attention, if he overfilled the unit, where's the fuel going to go? Straight over him. Okay, so that's why they used to bang the fuel point, the overflow line back to the fuel point cabinet itself. But the main thing is you just need to vent it to clear some of the fumes away. It wouldn't necessarily go back there. You do have different grades and thicknesses of tanks. You've got J-type and K-type. They basically take different pressure limits as such. So if you've got a tanker driver who's not paying attention, you might have a J-type, which is a lower capacity or pressure tolerant tank. It'll have a relief valve just over the top, so it'll split in there, so that's where you need some leak detection. So if he's not paying attention to that, you know, a lot of alarms and everything going on. Again, the most important thing that happens is, and to have belt and braces type arrangements for, are fuel leaks and secondary containment. So that's one of the most important things that we're always wary of with any fuel storage and delivery systems, to have suitable leak detection. And the last thing you want, for instance, if this is on the roof, in a plant room or a container, and it's bonded, and no one's put any leak detectors in there, they're not connected up properly, the connection of the fuel feed line to the generator has to be flexible for obvious reasons. Set's moving. If that fractures, tank fuel drops, automatically starts up the duty standby pump to feed the system on there because there's a demand. It's trying to top it up so you can feed the entire contents of that bulk tank into that plant room or container, and it has happened. So, leak detection at suitable points. You can bund the tanks, you can bund the overall system, the whole container itself or the whole plant room, or just certain sections, but either way it's the what if scenarios. What happens if this flexible fractures? How is it going to be detected? You know, to ensure that you do not end up feeding a complete tank into a leak. Okay?
Just
now,
going back to the car, is this why we normally we oversize the generator by something like 30% to 50%?
okay, why would you do that? Is that consideration to future demand?
No, for the load.
Ah, that's the key thing. Load step requirements. It's very much a question of what equipment you're supporting and its tolerance to the voltage and frequency limits. You know, what tolerance it can accept. If it's an MRI scanner, you've got very tight tolerances of performance. But normally, for instance, the G2 or the G tolerances are very important as well, and they're in section 5 of ISO 8528. They give you the voltage and frequency tolerances, and I'd always default to G2 unless sensitivity of the equipment dictates otherwise. Because if you've got, say, let's just pick some numbers. If you've got, say, 500 kilowatt pump, okay, how are you going to start it? What's your starting system? You can have a direct online, and with a direct online starting system, you can have, what, 6 to 7 times full load current, can you? Okay, then you've got star delta, something like 2.5 to 3, isn't it? And then you've got soft start, and then you've got inverter. So that, again, impacts directly on your sizing of your generator to take a step load, okay, within a tolerance band which you've stipulated. So if it's G2, you can take 20% voltage dip, 10% frequency dip. If you're saying G3, and you're starting, you know, it's your starting system and the amount of load you're putting on in each complete step, which in turn affects your unit. If you're giving me a performance criteria or a maximum dip and voltage of frequency and recovery time. So that in turn affects the engine alternator combination.
I don't think anybody in this room goes through all that. Well, basically, we all oversize it.
Yeah, but you're being, to be frank,
we all do it.
You're being safe by doing that. But the thing is, you see, what you've got, if you go onto Cummins Power Suite, this is exactly what I use. I used to work for Cummins 6 or 7 years. I'm most familiar with that. You can size a generator. Would you like me to skip and show you a report on that? Yeah? It's called Power Suite. Now that gives you an idea of what you're looking at. Size of the unit, what you can do. Now I'll do it by hand or I'll use the report. The report's the easier element to use. So what you're considering is two key elements. The alternator, suitable size of alternator, i.e. the amount of copper it's got in it. You got obviously excitation systems, you want a PMG and AVR, again which gives you the best performance. Or the A-rep system, which is additional windings in the stator, which is still independent, because the old type generators, they would take the feed, the excitation feeds off the load line. So if you've got a load that's dropped on, it's like a cascade effect. So you need independent generation. So in other words, your exciter section is independent of what's happening on the load supply side. So that's key. Please just ask the questions. Hopefully this is being suitably understood. So for instance, you've got a fire pump there. This system, this was selected based on your voltage and frequency. So you can see here, it's giving you the limits for, and that's the key thing. It's your load, what it is, pump, your starting system. Whether it's an inverter driven unit, what type of inverter, what performance, they're all high performing these days, but compared to a direct online, compared to a star delta, you know, that all impacts on what the engine alternator will see and the combination that you require to overcome that load. But you might have 3 or 4 loads. You can see on the top left there, you've got 5 load steps. All of them there indicated that's a frequency dip, actual 1% frequency dip. Okay, you can see on there as well, you've got the voltage dip, so you've got a 9% value on that. The actual limits are G2, 20% and 10%. So you can see, you set the parameters on these software programs, it can give you very much an idea, and it'll also break down all the starting loads, everything you're going to see, or that engine's going to see throughout the steps. So you can literally, gives you the full motor breakdown, you know, the shaft kilowatts, it assumes losses through that, so you know what electrical input you need to give you the 55, what size is this? Yeah, 55, this one is kilowatt motor, I think. So, you know, there are programs that will certainly assist you in doing that, but then you've still got to apply the criteria or the consideration. If you're starting those systems, how long do you want them to run for? What's your cap on the actual total amount of running time you expect per year? Is that going to be a straight load, or is that going to be a variable load? Now that in turn impacts on what you need to do with keeping it within the rating framework. Okay, there is a sub caveat of prime, which again it's very important. PRP's average variable load. There is a sub caveat for the prime rating itself called LTP, limited time prime. So for instance, on a pumping station I've looked at recently, you've got 8 500 kilowatt pumps, and what they want to do, they don't want it to run for an unlimited period. They're saying literally only run maybe 200 hours per year absolute max, which pushed it to emergency standby, because you've got the 200 hours cap on that. However, it's constant load, so it's not variable, it's a solid constant load, they're saying. So the sub caveat of prime, LTP, basically says, the ISO standard says you can run 100% of its rating for up to 500 hours per year. And guess what? The Cummins product will allow you to run, actually, goes over and above the standard. It says you can run up to 750 hours per year. So again, the knowledge of the different manufacturers and their limitations allows me to then actually make the recommendation of the best engine alternator combination to fit your requirements. And the thing that's important that we all want to do to cover our asses, so to speak, is pin the tail to the donkey with the running parameters, the limits, because these things get forgotten and changed. But what you're doing is you're nailing it so that everything else, you know, can be recommended based on those requirements. Because often on data centres they'll do day 1, day 2, day 3. You know, you might oversize your unit because one, you want to consider the fact that the power's going to go up, not down, and you want it to last for 15 or 20 years and not have to bring another unit in because it's struggling. So whilst you're taking size of the set and banging 30% of it, I'd say that's a very good rule of thumb. But really, probably for peace of mind, you want to go into it in a bit more detail and derive it, and you know.
So you're talking about data centres. What about leading power factor?
You
the rating curve of 0.9 leading goes down to by 40%.
Yeah, yeah.
So you're overrating, you know, to oversize it for the leading power factor from the.
Absolutely. One of the biggest things was the blade server issues, where normally with the generators, just wondering whether I don't normally get those sort of questions, but you've got a depth from a curve, it's something like this. It gives you parameter, really I'm not going to do it justice. Basically what happens, the performance of the alternator works between 0.8 power factor, lagging and unity. So lagging and unity, okay? Where you have a leading power factor, what that does is the tolerance for an alternator, for a standard engine alternator combination, it can only stand a very small amount of leading power factor. Now, a leading power factor essentially means that it gets unstable. The excitation of the actual the rotor itself starts shutting down, and you actually get unstable and it runs away, and it causes overheating and damage, thermal damage. So the key thing is, over and above everything else, if you've got a leading power factor, basically what happens, you get a bigger alternator, more copper, it can actually stand that factor and not have any issues with thermal damage. So it can cope with those loads. But again, it's understanding what the engine and the alternator combination are. They're coupled together, but they're obviously tied in. The interrelated effects with the leading power factor, what happens, you get a larger alternator to accommodate that load, and then what sort of load steps you're looking at and what the duration of running you're going to require related to the ratings. So how big your engine driver needs to be, with consideration maybe as to what your future demands are going to be in the next 2, 3, 5, 10 years, what extra allowance you require, because you know, want to play safe.
What you could do, you could put PFC in the bypass of the UPS and not oversize the generator.
You could, yeah, assuming you can't do that, you go up alternator. What happened quite a few years ago, that for a lot of the initial data centres, the blade servers were a real nightmare. So on a lot of sites, we actually did give oversized alternators to accommodate the leading power factors, but all that issue dropped off because by design they started the bypass element, so the sets didn't see that, and the blade servers have naturally progressed with their efficiency and not so much dirty, dodgy power, basically, because that's the key thing. So, you know, again, knowing what the issues are allows us to, by design, select and recommend the most suitable option given your requirements. So, go back to the G tolerances. It's probably best for me to highlight that. So, all I would say to you is always default to G2. G2 unless the sensitivity of the equipment dictates otherwise. G3 is 15% voltage dip, 7% frequency dip, and G4 is you tell me what you want over and above that. That's how it gets. But the implications, if your load, say a 500 kilowatt unit, and you tell me G3, what that essentially means, bigger alternator, probably a bigger engine, to keep the load step within that tighter tolerance. And that's the key thing. So you can see how they are. Often what happens, you'll get customers and consultants saying they want G3. Well, they're only starting at pumps and general systems. It's completely over the top. And obviously you need to sort of make them aware of that, just to see whether they really want that and what the implication is if that is the case. Because obviously if you run through those sort of things, we're the experts, so given the implications related to what they're asking over and above, given the load and detail, you know, starting systems and the actual loads, that sensitivity of them that we've gleaned, the information, and they can make an informed decision still. Again, All it is really, and all I often do, is give them the pros and cons. You know, why have you gone for G3? What's the equipment? Would you, G2's the norm for this. Do you really want over and above? Why? You know, this is the implication with the size of the engine alternator. Just covers the bases really. So really I've probably covered that reasonably well. Genset itself, that's your, let's just go through here. Right. Alternator, typically that will be 95% efficiency and higher. Alternator, then your engine block, and then your fan and your cooling matrix. It's a push-pull fan arrangement here. The key is delivering the inlet air so that it goes across the unit in this fashion, delivery of the air. If you're delivering the air into the plant room above, it'll shortcut directly onto the cooler matrix and cause hot spots. So the issue is handling the air suitably to deliver it at the back end of the unit. You get an actual heat pickup. Say you're outside ambience 40 degrees centigrade. If that's 95-96% efficiency given size and running up 100% of its rated load, you'll probably get a heat pickup of about 2 or 3 degrees C across that unit. Across the engine block itself, you'll probably get, in turbos, probably a 5 to 6 degrees heat pickup. So essentially, if you're outside 40, your heat pickup or your air on temperature will probably be up to about 49 degrees centigrade. Through that cooler matrix, you might then get a heat pickup, the heat dump across that for the intercoolers and main jacket cooling. You might get an increase in temperature of about 30 degrees centigrade. So either way, you're talking 70s, 80 degrees centigrade discharge temperature, which needs to be considered when you're a maximum ambient or design ambient. So all these things again need to be considered. You don't want to be discharging air where someone's walking. That's just a little bit too much of a large hairdryer really. So, in a plant room application, notice the genset itself, it's isolated. It's mounted on AV mounts here. You've got a bellows here. You've got a flexible canvas here. So it's isolating the noise generation, the vibration source as best it can so it doesn't transmit through the building, the structure itself. The size of the inlet attenuator and the discharge is dictated by a combination of two things. It's a function of cross-sectional area required on the inlet and discharge and length of attenuator. The more onerous the attenuation, say 75 dBA at 1 and then more onerous 65 dBA at 1, the implication difference with those two, ignoring cost, is length, because the ear picks up most of the low frequency sound. Unfortunately, often the way of absorbing or attenuating the low frequency sound element is a function of length more than anything. You do get different air gaps between the vertical splitter blocks for each one of these attenuators, because if you looked end on of that attenuator, ignoring the louvers, all it is a series of blocks and air gaps between them, literally like a sandwich. You block, literally that's all it is. And you've got perforated screens on this side, and normally it's rock wool, I should say. Rock wool that's absorbing the sound. So that's normally what you'd look if you took the horizontal weather louvers off. You'd look through and that's all you'd see. So the reason why there's a damper here and there's a damper there is your diesel generator is basically sitting there in anticipation of needing to start. It's got jacket heaters there on the unit that are constantly running and topping up, basically thermostatically controlled. Now when that set's running, it's probably 80s return temperature to the engine block, okay, early 80s. What basically happens with the standby rated unit is the thermostatically controlled heaters will probably maintain temperature of the cooling system to about halfway house, 40-45 degrees centigrade, because it's wanting that set to be ready and to take the most load acceptance and be up to running and cracking along. For instance, it's equivalent to your car in the middle of winter time. You know, you go outside, very cold, you're not going to thrash it straight away, it's not going to like having loads put on it. So basically that set's always sitting there in anticipation of needing to run, and it's kept at the halfway house temperature, so to speak, so it has the best load acceptance even though it's not up to running temperature. So the key thing is they call it cold load acceptance temperature, and that's engine blocks up to 45 degrees centigrade. So if you get a set in a witness test or something and you're coming along first thing in the morning, that's the best thing to see what the performance is like, because if you, in context of operation, you know, that's the closest to it. When the set's up and running and up to return temperatures of 80, 85 degrees C to the engine block itself, that's a, you know, it's a nice running temperature. So its load acceptance is actually going to be better. Load acceptance and recovery, because it's fully up to temperature. All right. So you get quite a bit of radiant heat from there, which keeps it nice warm to space. So if you've got a slight breeze blowing through, the last thing you want is the jacket heaters on all the while. So ideally what you'll do is you'll have motorised inlet, maybe gravity discharge louvers that will basically enclose that room. So it's easy to work in, more controlled environment, and your jacket heater's not working as much as well. These are spring open motor close. Spring open, in other words, they'll foul open so the set can still run. Gravity dampers, basically they're just blown open by the airflow itself, and they'll sit. You get more of a pressure drop off that. So if you're talking more within limits of pressure drop, etc., you can have those spring open motor close as well. So again, keeping it within limits. Now, the performance criteria of the fan that's located there, often what happens when you put them in plant rooms, in fact I've drawn it. This isn't a plant room. Normally they like putting it in the sub-basement, which makes it fun. That set mounted full push radiator for the KTA 38 G5 will give you 11.2 metres cube, or require 11.2 metres cube per second of cooling air. Combustion air is 1.123 metres cube per second. So basically that's summation of those two being drawn in the inlet here. If you're going into that plant room, you'll need to attenuate. That pull pusher fan will draw air in from the path release resistance. Given your discharge temperature, you have to duct it away, because the last thing you want is it recirculating and then shutting down the engine. It's effectively derating it, drawing in higher ambient. Okay, so you need to duct that discharge system away. Okay, so ducted discharge, but you can have multiple air inlet paths as long as ideally you're delivering it to the alternator end to have a nice, clear, sort of relatively laminar flow across the unit itself to avoid hot spots on your exchanger, any problems with the alternator, etc. So you can put an attenuator there, delivers air into the room nicely, draws it across. That fan performance and airflow is based on 250 pascals external resistance. You can easily lose 50 pascals for the inlet and maybe the discharge. Now you can put a discharge here, for instance, but if you put the discharge there, sorry, you've attenuated there, put your attenuator there and then turn it. If you've attenuated there, you'll get noise breakout that will actually go into the ductwork. So if you attenuate it there, you'll have to line the ductwork. So by design, the best thing to do is basically put your attenuation at the leading point of the room itself. So you can duct it, but you only need single skin ductwork and a turn-in section really to clear it. So again, by design, you can save a lot of cost and optimise the layouts, etc. You might have air coming in at the same end. Duct it to deliver it, the inlet air to the back of the room. But either way, from that point to that point, wherever it falls on the wall, or ideally the other side of the building, because if the inlet and the discharge are right next to each other, what's going to happen? It's going to draw the air in straight away. You're going to get recirculation problems, shut down on overheat, depending on the circumstances and situation. But either way, it's certainly not going to run properly on its design.
If the set's external,
yeah.
there's been issues in London with noise, say data centres or premises, you know. So what do you normally see for city centres is the normal DBA of 1 for generators?
It's a cracker actually. You get the hand tucker reports and other consultants as such. Basically what they'll do for a new site as such, they'll say, okay, take the sensitivity around the building, say, building plan view. They'll probably monitor there, that whole area. They'll take day and nighttime figures. They'll work out, you know, what's the average, you know, so the daytime might be something like 75, but the nighttime might be 65. In a lot of cases, what they want to do then is say, okay, but we don't want that set, or those sets, if they're running, to contribute to the overall noise level at night. So they'll then take 10 dBA off it. So they'll say the sets need to be 55 dBA, which is horrendous with regard to extra footprint area that's required for the inlet attenuators, the discharge, and the silencing systems. However, these points here, the most sensitive, well, put it this way, if your set's here, or right in the middle of the building, and you've got literally 20 metres away from that unit, they're saying it needs to be 55, maybe at these measuring points here. If that set is sitting right in the middle of the building, and you've got 20 metres drop, or 20 metre distance, you've got a natural loss over that distance anyway. So over about 20 metres, you've probably got 18 to 20 dBA drop. So actually, what that means, you add that to the, you know, that's back at 75 dBA at one individual. So you can extrapolate, and then you can actually have a unit that's taking a smaller footprint. So again, as with motor loads, as with starting systems, anything else, you manage to get that additional information, what you can do is nail it and supply a suitable unit in context. So you can supply a 75 dBA unit at 1, 75 dBA at 1, knowing full well that it will achieve the criteria of 55 at that boundary point.
Yeah, and just comments that on projects I've done, that's all been very carefully worked out, and then the builder put on a roof that had no acoustic properties whatsoever, really. So the whole thing needs to be considered.
You're right. Actually, the other thing to bear in mind is if this unit's going on a roof here, and your sensitive points of residential neighbourhood here, say in the middle of the room, you've got natural shielding anyway, and you've got the diagonal drop as well. I came across that when I first got involved with Cummins, Norton Folgate to a One Bishopsgate, Broadgate Tower. We had that sort of consideration because the figures were exceptionally onerous, but again, you've got the diagonal effect and also the shielding elements to consider. So again, it's where you involve the acousticians that will really, you know, clarify these elements, what's acceptable and not, but it's getting the details so you can understand and recognise it and come to the right conclusions in context.
I mean, another case that I've seen is, which is really unfair for us engineers, is that a data centre in London was there first.
Yeah.
The chillers are on the roof.
Yeah.
They have a DBA design for the design load at the time of the noise levels.
Yeah.
They go and build apartment blocks next to the data centre. The top floors overlooking the chillers. During the summer, when they've got the windows open, they've got the blooming noise. They then complain to the data centre company for the noise.
Yeah.
They were there first, and then the data centre company's got to pay for attenuated screens.
That's like building around an airport and complaining about the noise, isn't it?
Yeah, but it's just unfair, really
yeah.
unfair.
But again, there might be something that could be done retrospectively on that. It always is the case. And quite frankly, the fact that we've got so many concerns with attenuation and the levels of as such, it shows how affluent we really are. You know, how sensitive we are to a little bit of noise in the evenings and such. And the other thing related to this is there's a clear distinction. Sometimes these are life safety units. And if they're life safety units, they recognise the likelihood is very low that they'll be needed. So they might actually turn around and say, okay, the nighttime figure is 65, give us one at 65. Because they won't really care. But if it's a tenants unit, with the likelihood of a longer running period, it's more onerous. That's what it tends to be honest. So again, I'll feed back off from the consultant, what is it, life safety? And they tell me the levels. But for a life safety unit, ask the question, what you know, is an acceptable level, and they often do differentiate, but it's pointless if you've got a plant room there and you've got the first unit of life safety dedicated and then a tenants unit sitting in the same plant room. You know, it's in context whether it's actually going to work or not, again, because they might wrap it overall. This is the noise level maximum required, because you've got both units running in there. You can't easily differentiate, of course, and if they're both in the same plant room. So I've kicked that to death, really. I like things as simple as possible. Types of radiator. You'll notice on that one, basically, I like a set-mounted radiator and I'll use it wherever possible. With these sort of designs as such, for drawing the air in, you've got a 250 Pascal limit. Often we get questions about, with consultants saying it needs to be remote cooled. Well, okay. How much air, if you took away that radiator and put a plate heat exchanger and then banged a roof-mounted radiator up top, how much less airflow do you think you need to pull through that engine compartment? I thought it'd be, when I first started, I thought, 20%, 30%. No, it's more like 50 or 60% you'll still need to pull through. The reason being, your heat pickup. If you think when the set's running, I said 2 to 3 degrees on the alternator, 5 to 6 degrees on your engine block, you don't want anything more than an 18 degrees delta T in that room, realistically. Because again, I've got to consider combustion air with a heat pickup. You've got to have a sensible amount of air movement through there. So essentially you could be only saving 50% of the airflow that you normally require. And if you've got a remote cooled unit on the roof, multiple rads, attenuation issues possibly, 30 grade big attenuator on the top, electrical requirement for those radiators, you're going to have a cooling feed and return system. You'll need a simplex or duplex pump, depending on how concerned you are with resilience on that. You've got your plate heat exchanger there. You'll need an expansion system on that. You've also got a lot of extra cost. The single pipe system. You might have trace heating requirement on the top there with that pipe, with that with the cooling system, feed and return. And then, because you've taken away the push puller fan, you've now got to have an actual fan in there and an actual fan in there. Putting the air in, drawing it out. You need to be modulated, because the last thing you want is a pressurised room, so you can't even open or close doors. And you'll still need attenuation in there. So all you've done by moving that set-mounted radiator is increase your interdependency on other kit and equipment. What if it's an 11 kV unit? Those fans will run at LV, that pump will run at LV. So then you've got to actually go to a switchboard, then via a transformer to then feed back to those units. You know, I like it simple. Set-mounted radiator. You've got crank, pulleys, straight off the shaft of the engine itself. That'll do me. Nice visual check. No burnout of any motors. You don't really know what the conditions are on them. You can have a quick visual check and it's ideal. Halfway house in between that standard unit and those extremes. If the actual pressure is in excess of the limits of the fan, 250 pascals, what you could do is draw in the fan to deliver air at a neutral point and use the whole of that 250 pascals on the discharge section. You've got a halfway house there, but it has still functioned probably if in the highly likely event that fan did fail, given the load, given the ambience, it might still fall within, you know, still function okay, but at least it's a halfway house and you've got a hell of a lot less interdependency and cost. So again, I always like it, keeping it simple wherever possible, but sometimes you have to use electric driven fans for your cooling system across the unit. This gives you an idea of your fuel tanks. I've touched on those. Local regs. The key thing over and above everything is really what happens if scenario. You've got let's just say set on a roof here, in its box, you've got fuel feed line, you've got the bulk tank here. You'll have a duty standby pump arrangement, feed in there. Your max that unit's a 1 MVA, so it's using 220 litres per hour maximum. You've got a freestanding day tank, 4-hour unit, sort of 1,000 litres, something like that. your fuel feed comes in there. If you're running 100% load and you've gone to your low level and it's given a demand, how much do you need to rate your pumps for? If you rate it for the maximum load of that unit, say 220 litres per hour, all you're doing is holding the level in that tank if it's running at 100%. So basically you need to rate that normally twice working, and if you've got additional units on there that you're going to add for a tenant, in addition to say a life safety unit, again you can size that delivery system initially for day one or day final, whatever. Again, it's all these considerations that then come into play. But this is a positively pressurised line, therefore double skin through the building. That may be a single skin tank in a bunded plant room, or it could be a bunded tank itself, come as a pre-built bunded tank unit. But either way, secondary containment and leak detection, always important and key. And again, it's the what if. With this riser, you actually have a sort of elbow section there in a leak detection. So if that inner skin fails, you want to know. You want to know there's been a leak and where it is, to track it, to find it. The biggest single thing with this legislation is, and I did it on one side, you have a customer that says, I don't want double skinned, leave it single. Okay, it's fine. We had to ask the questions of duty of care. If they have the leak, where does it go? If it means that it just contaminates their offices, their basement, and doesn't get out into the watercourse or anything, then you're fine. That's up to them. That's their decision, their cost, their clean-up. But if these things do go into the watercourse, or you transfer them from A to B, and you've contaminated some land, that's when you might as well just give them a blank check. And it's coverage of duty of care as well that always is one of the key things. Asking the right questions, getting the right answers, saying and recommending, and obviously then tying them in with the legislation, the DEFRA requirements, the transfer systems, the capacities required. Often sets on the roof, certainly in London, they'll have a dump requirement, go back to the bulk tank. So the fill on a bulk tank may be this size, say this is 1,000 litres. The fill requirement on that bulk tank, of course, is going to be its capacity minus 1,000. That's its 100% fill. Because otherwise, if you get a dump situation where you've got a fire in that unit, you'll have it spilling everywhere. Again, all these considerations which sometimes, until you really look at it and go into detail, you don't see. Electric starting systems. I've never done air starting systems, to be honest, but you can. Batteries are very reliable. Two things you need for a set to start: fuel, batteries. Simple as that. If they're both there and the batteries are sufficiently charged, normal demand is when the jacket heaters are running on the engine, you've also got a trickle charge onto the battery to keep them nicely topped up. Normally after starting, the voltage recovery is over a certain period of time. As a preventative maintenance measure, often they'll monitor the voltage recovery times and start saying, okay, these batteries are on the way out, replace them as a preventative maintenance measure. You can have two sets of starters, you can have two sets of batteries and chargers. You can have them all sized for 6 starts, 3 starts, but either way the sets are so reliable these days. After 3 start attempts, irrespective of what capacity you've got in your batteries or transfer, changeover systems you've got, dual sets, I would say someone needs to go and manually investigate. It alarms and they have to clear it on the control panel of the generator itself because something's wrong for that set not to start at 3 attempts. You'll have a 10-second crank and you'll have a 10-second dwell before it will then start again. The reason why, those startometers get hot, and so they just need to, you don't want to burn them out. And normally with larger units you might get 2 starters or even 3 starters. They'll gang them together because again it's to do with life and resilience. You might have a set with 3 starters, but if one fails it'll fail safe. The 2 starters will still have enough capacity in them to still turn over the unit. That's often tested at hospitals as well. So again, belt and braces, resilience, failing safe, all these sort of aspects that are considered. It's all silencer systems. Basically you've got the bellows and then you've got a silencer system, could be primary and secondary, could be your main silencer off each one of the V banks if it's a V unit. Then they're brought together and then they go to the secondary silencer and they're routed wherever. You keep within back pressure limits. It's like putting a banana tailpipe on, exhaust pipe on the car. It'll fire, it'll have problems. That's the thing, you keep them in the back pressure limits. Often most sets will work between up to a limit of 10.2 kPa. You lose 60% probably of that overall limit within the primary, secondary silencer arrangement and turning them, and after that it's the flue system, the horizontal run, the amount of turns and everything, which then dictates overall size. You have skin temperature limits, sometimes touch, because sometimes they'll run through corridors and people can go up and touch them, and they'll have limits like 70-75 degrees centigrade, which then dictates the thickness of insulation you would need on that exhaust pipe itself as well, on the exhaust flue. So again, these can end up quite large diameters depending on the routes, turns, and back pressure limit that's left on the units. But in a plant room, you'll normally bang them above the silencer if you've got suitable head limit, and actually even simple one, as I showed you here, this arrangement. You have the exhaust silencer basically discharging out above here, and it's mixing with the discharge air, so it helps it disperse. But when those sets start up, there is always normally a big plume of black soot smoke. The reason why is because it's banging the maximum amount of fuel it can in those cylinders to start that unit up as quick as possible, because it's an emergency unit, simple as that. And that will clear, it'll stabilise very quickly. You can have low smoke starting systems, but at the end of the day, that's a compromise on how quickly that set gets up and running and ready to take load. So again, you've got various other systems.
What's your take on catalytic converters?
You can have cats. The best way of old hospital spec C44 used to say, I want a two-stage cat converter. That's like saying I want a car, but you're not going to tell me the engine size or the performance, are you? That's the thing. You can have two-stage cats, you can have selective catalytic reduction, which is urea injection systems to reduce your NOx levels and all these sort of things, which add loads of extra cost to it. But the key thing is with any catalytic converter, you want it as close to the discharge after the turbo as possible, so it gets hot and up to temperature as quickly as possible to actually function properly. Obviously, you know, you've got the same sort of consideration with cars to an extent. However, what they'll normally do, a catalytic converter, you'll bang it, maybe extend this primary silencer by another metre, and even have a cartridge type which you can take out and replace, given the performance requirement of that unit. Because often the hospitals will say they want it, and we'll ask the question always, well, what performance do you want out of it? And then they'll just not have it. Because often a lot of these specs don't get updated, they're just getting cut and pasted from year to year. One of the other things in the hospital specifications are they want NiCad batteries. NiCad batteries were very, and still very good, because you get a high output for the weight, and they used to be very useful on oil rigs and all that. But Planté, sealed lead acid type batteries, gel batteries, and all those sort of things have developed very well to even supersede those, because you've obviously got issues with disposal, NiCad and all those sort of issues. So lead acid's always the way to go, to be honest.
Have you had any constraints on flue systems, like for the NOx levels and PM2.5s?
Right.
What do you see coming in cities?
They ask the question more and more, to be honest. There's one site at the moment I'm looking at where they're asking for a selective catalytic reduction system. They've got an overall NOx limit for that site. So it's like, okay, what's the limit? They've told me what the limit is, but also you've got to base it on a certain amount of running hours per year, what you expect. And then, so I asked them to do it in that fashion, so I then work back and say, okay, it relates in turn to the actual performance of the selective catalytic reduction system that I can offer them. Because again, at some point the cost comes into play. You don't want to give them something that's well over the top when, a much more standard, smaller unit would suffice. But that comes into play more and more. The key distinction is portable units have much higher requirements on legislation, on emissions. The rationale behind that is they'll bang the portable units anywhere, they're on a site, they're not really getting rid of the emissions. If it's a permanent installation, like a plant room, like a high-rise building or whatever, then it's been considered, because you've got the exhaust flue that'll probably get to the roof and discharge it clear and away and disperse it, because the key thing really with the Clean Air Act is emissions dispersion, not control, but suitable dispersion really, where they consider local structures, where's the pipe, how it's directioned, and how it then clears. And that's related to the discharge velocity as well, because often with flue systems what we'll do, we'll work within the pressure constraints, we'll actually throttle it down the last couple of metres to actually make sure it's banging out at sufficient velocity to clear the building. Because if it's just dropping out of the actual flue itself, it can accumulate on a building where a lot of people like the sky gardens and things like that, you know, you can get a build-up of the emissions, which causes respiratory problems. Panels control systems. You've got deep sea, you've got DIFE, you've got COMAP. It's very much isolation of those systems need to be considered as well. You can never connect steel wide armour cables directly to an alternator. Quite frankly, it'll vibrate, it'll harden, work harden, and it'll fracture, it'll fatigue. So you need to have that transition as well with flexible cables. So if you've got, say, engine alternator combination here, you can have a set mounted breaker here. You'll need flexibles from that. If it's in a box, it might be to a wall mounted link box here, or they bring in flexible cables, but probably not. But that gives you a transition point between steel wide armour and flexible cables. It could be a freestanding breaker in a plant room. Flexibles, steel wide armour in. Nice transition point. But either way, isolating that unit so you've got no problems with steel wide armour fatigue, etc. And also stress. Obviously the steel wide armour is very rigid and it can cause stressing and fracturing of components inside, or the plate or the housing you're connected to. It's far from ideal, and also noise transmission. You know, you can create yourself quite a few problems, but again, key thing's isolation. Just gives you a rough idea. COMAP, PLC controllers. We've just secured an order last year, 1 Bank Street, just under 6 million. That's 5 2.5 MVA emissionised units, 3 in a plant room, 2 in a plant room. Attenuation level 52 dBA at 1 individual. The implication of that, as I mentioned with the attenuation on the inlet attenuator bank is 7 metres long alone. 7 metres. And it's offset, so you've got primary stage is sort of maybe up to about here, then you've got an air gap, and the actual splitters are offset. So if you look through, you can't see, because they're staggering the air paths again as well. But 7 metres, again, that's the key thing. You know, the set itself sometimes doesn't take up that much of a footprint because of the power density and everything you can get. But the associated components, you know, the airflow you required, you know, everything's getting very much more compact, but you still need the cooling air. You still need those systems. And, you know, you still need to attenuate these units, I'm afraid. So you can end up, you know, with quite a footprint. You know, the plant room's easily, well, it's probably all the way to the end of that building there. That's just the inlet and discharge systems associated with that level of attenuation. But it can be done. You've got kinetic floating floors, and you've got enclosures within the building section itself. Sorry, yeah.
Yeah, no, it was the chat about attenuation and about emissions and city centre restrictions,
yeah,
etc. Do you think we're very far away from large-scale battery storage? Because in the last year that's starting to be rolled out, and obviously that would remove attenuation problems, it would remove emissions. Is it something Broadcrown JCB do you think are looking into for future products?
We're looking at that. We do have some units actually at the moment. Say on a construction site, construction company will say, oh, I want a standard 20-foot power box unit, which is 1 megawatt, 1250 kVA, prime rated unit. It's a very compact unit. You'll see one of the photographs in a few moments actually. They might, on site, run that unit. They might be consistently running. There you go, that's the unit, bottom, that one there. It's shoehorned in, tight as anything, uses all the back pressure on a box silencer, on a roof, but it's very good, portable unit. But the actual power requirement on that site tends to, on a lot of the sites, will probably be only 100, 150 kVA kilowatts. So that unit's running well within its, under its normal limits, because normally when a set's running, you don't want it sustained running less than 30% of its rating, because it causes carbon build, it causes pass through the fuel into the lube oil. You know, it's not good. Overheating, it's not ideal. But the thing is, you see, what's changing is we're monitoring it. we've got telematic systems now which will actually monitor that unit. So what we'll do is we'll actually give them feedback and say, look, this is what your set's running. Are you planning to increase the load on this? Oh, no, not really. So you can halve the size of the unit. We've just saved you an awful lot of cost, and you know, you can monitor it more. So technology is moving forward with that. With regards to batteries, we do have also a unit that will actually, via inverter, a very small generator, it'll actually top up a large slug of batteries underneath the unit, or even a separate housing of batteries, and then the batteries will supply the power via an inverter for your site loads. So in other words, you set stopping and starting periodically to top up the batteries when they fall between min-max limits, again optimising it. So like your cars are at junctions these days, in neutral, off, as such.
Yeah, the thing I was watching yesterday was something the size of a container that go on the back of a lorry. And it's a zinc plate system, liquid battery system, that would retain its charge even if it wasn't used, and it was provided 2 to 3 days.
It is moving that way.
The office block, so it's whether JCB Broadcrown are kind of investigating that route. It might not be ready now, but 5 years from now, maybe.
We are looking at that. Often what's happening more recently is because of the drivers over in the States, certainly in the west side more than anything, California, they get horrendous penalties with using diesel, with emissions and all the problems on that. So you've ended up with gas sets essentially being semi-hybrids. So gas sets are actually being used now for standby power, which is really quite surprising. You can see the trend, but originally there was such a gap because gas sets, their load acceptance capability is not very good, certainly compared to a diesel. As I said, the NFP 110 spec, diesel will take 100% load step. You try and put 100% load step on a gas set, it'll stall, no worries. Even 50%, some of them will stall. But what they've done now is they've ended up much more hybrid, so they can ramp up very quickly. And then you've got your load management systems that'll actually reinstate and control it, so it works within the limits of that because of the emissions concerns. Now, going back to batteries at the moment, we've got instability in the grid, we've got problems, we've got obviously the nuclear power stations, we've got the various connections to the continent and the stuff coming in for the coal-fired stations being shut down. We have got problems with that, and they've been producing a lot of sites where you'll have 20 megawatts of power, and it works out most cost effective with those units are multiple for 50, 500 kilowatt units. So you've got standard enclosure units like these, big farms of them up to 20, top unit on the right there, say something like that, or that one. 20 megawatts of those units, 48, 50 units on a site, and you know, they're splitting the emissions out. They're shoring up the grid. Now, to go back to your original point about batteries and things as well, they're looking at batteries now as faster reacting because the grid's becoming a lot more unstable because you're taking a lot of these large power stations offline now. So when it starts to go, it goes quite quickly. So they've got all these small units, a lot of key sites, and they're reconfiguring the power. They're doing it in a very smart fashion. However, batteries are coming into play as well to keep the grid within the voltage and frequency tolerances and limits so you don't get cascade problems. So the battery units are very fast acting power reserves. So you're literally getting 40-foot containers packed with batteries, as you've rightly said, that are coming more and more prevalent. As to whether the financials will stack up, certainly for the grid, I don't really know. They are supplying some already, so they have to. However, to actually replace diesel sets and buildings and those sort of things, not sure yet.
Is there not an opportunity to generate a bit of income with these things, with demand response and the like?
Yes.
Because I think, you know, to me, a standby generator set is a lump of capital set. They're doing absolutely nothing.
Absolutely bang on. Normally, what they'll do, you had Flexelectricity and a lot of the others for sort of the last 5 or 6 years. They've been going around and even looking at exhaust flues to find out whether they're boilers or whether they're standby diesel. And okay, when you think what they do is they'll connect you up, and they were paying something like you were getting if you did it directly with the DNO, which I think was probably hard to do really. With via Flexelectricity, you probably get something like £20,000 per year income. This is old figures, don't know how much it's changed, per megawatt availability, let alone running, per year. 20,000, which is not bad. But you didn't need to parallel with the grid. If you're drawing in power and they say, start your unit, doesn't matter if it's not mains paralleling, all you've done it started that unit running your systems on your embedded generation and freed up that power to be used elsewhere. So you don't necessarily need to export or anything, you just run in island mode, supporting your systems. So again, that's what actually happened, and it's happened very, very much more. It's going to get more acute, I think. They're knocking about with triad values and figures at the moment though as well, taking those down. It's a bit volatile what's going on at the moment, really. There's a lot of uncertainty in the market with regards to DEFRA emissions. The documents come out and they're limiting certainly the diesels and the gas emissions as well, again, which is skewing the market, and then they're taking away some of the subsidy associated with the smaller generating companies. So often you've got the standby power. Life safety is always critical and always important. That could possibly at some point be supplemented with batteries. Why not? It's a fair question. Batteries via an inverter to give you the 3 or 4 hours. I don't know how cost effective that really is. I've never done the check on that, but that may well happen. Because battery technology is certainly moving on and coming on at a good rate. Sorry.
It's interesting where people use drops, diesel rotary UPSs. As soon as the frequency changes, the diesel rotary comes on, and they can feed that straight back to the grid and make quite extortionate amounts of money.
Yes.
Just using it for their normal operations.
Yeah.
That's what I use the rotary system for.
I'm really sorry. I've rabbited on. I'm running out of time. I've got to try and get a train at 8:25 this evening. I'm so sorry. If there was a later train, I'd take it. But I need to get back to Peterborough.
Yeah, that's not good.
Yeah.
CHB?
I used to. The company, I'm trying to get them to do it. They did one job a few years ago. They didn't go as well as we'd hoped with some of the interfacing systems. However, I did that for 5 or 6 years, so I'm trying to get them involved on that. However, the best thing that's happening at the moment is the store sites are moving towards gas. So we're looking to supply and package gas units as well, which again gets the ball rolling nicely. Then you're only mucking about with food heat recovery systems. But quite frankly, that's more intricate design to optimise it, using the hot water, maximising your efficiency, especially if you're running it 24/7. Used to do Royal Mail Office supply units to that. They call them IMPs, Integrated Mail Processing Systems. They get a glitch on the mains, take 3 or 4 hours to reboot, loss of production, major costs. So they run the gas sets 24/7 and use the hot water and space heat as well with the waste heat, which is very efficient, up to 95% efficient. In the middle of winter when you're taking everything out, and there was condensing flue system as well, so they literally snatch everything they could into the airflow, into the air handling unit, which is very good. We'll see as to whether Broadcrown moves that way. JCB.
I think we'll go on for the next couple of hours if
I'm sorry,
stop
yes.
him now, and he does need to get his train. So if there are any specific questions relating to the presentation tonight, we will put this up on the website as usual. We'll put Will's contact details up, so I'm sure he'll happily take any further questions offline. Our next event, well, first of all, if you could just show your appreciation. Our next event on the 19th of April is our AGM, followed by a presentation by Paul Chatwin on wellbeing. As it is the AGM, if there is anybody in the room that is interested in becoming a committee member or becoming involved a little bit more, please feel free to stay behind afterwards and pass on your details, and we'll happily see if we can get you involved. Okay. Thank you very much.
Thank you.
I've got some other cards here, so please help yourself. Sorry, you're the man that's dropping me off, aren't you? Thank you.
Not so nice.
I remember I did that once. I came back from London, got off the station at New Street, said, what time's the next train to Peterborough? No, he said 7 o'clock. I said,